What's going on, YouTube? Sharky here, and today's video is about about a particular question that I struggled with for a long time. It took me the better part of a year to really answer this question for myself. I asked quite a few people how to figure this out, and not too many people had an answer. So that's probably because it's a tough answer. It's a tough question, and there's a lot to it. There's a lot of prerequisite understanding and knowledge about RF, DC theory, AC theory, to really get a good picture of what's going on. And that question is how to select capacitors for your transformers. So a lot of people, they see these videos and they see all the parts together, but they can't see the value on the capacitor, so they don't know how to copy it. And unfortunately, it's not easy. But once you understand the principles behind it, it actually becomes pretty easy. So before you watch this video any further, I strongly recommend getting a grasp on AC theory, how capacitors and inductors work with AC currents going through them. It's not an easy topic. It's pretty mind-numbing read. But if you skim through it, you might pick some things up. If you skim through it, you might start to realize how it really applies to the real world, how it applies to radio, how it applies to power lines, and all kinds of stuff like that. It's a strongly recommended read. Even if you don't understand that and you don't know what AC theory is, you could probably watch this video and pick up on a lot of it and get the gist of the subject. But again, strongly recommend looking into that. So, in order to know what capacitors to put on here, we have to understand some of the basic principles. So first we have to understand what this is doing. And then we have to understand what the capacitor is doing in conjunction with this. So let's start with the transformer and what its job is. Again, AC theory, if you skim through it, you'll probably find a part where what a transformer is and what a transformer does. But in RF, you got to think about it a little bit differently. This isn't quite the same thing as like a AC mains transformer that you'd find in, a power supply or something. The primary job of this transformer inside of an RF amplifier, and I know a lot of you are going to be into 27 megahertz, so that's what I'm going to assume. I'm going to assume we're talking about 27 megahertz because things change with frequency. So the primary job of this inside of an RF amplifier is to transform the impedance from one impedance to another. So the primary job here is to transform the impedance of the transistor up to 50 ohms. That is pretty standardized throughout all of radio frequency operation. And it does that by having a difference in windings. So on one side you'll have, in this case, you'll have one winding on the transistor side, and that's usually your low impedance. That's pretty much always your low impedance side, unless you're working with like high voltage devices or something. But anyway, your transistor is generally going to be your low impedance side, and then your 50 ohm output is going to be your high impedance side. So the transistor is pretty much always going to have one winding. That's this brass tube, goes through and connects on the other side. So that's if this is on the output of the transistor, that's your primary winding. These brass tubes going through here, that's your one-turn primary winding. And then there's going to be a piece of wire wrapped through those tubes, and that's your secondary winding. Typically, there's going to be more than one turn, probably 2, 3, and occasionally 4. What it does is it takes your high current, low voltage from your transistors. So most of the amplifiers that you guys are probably familiar with are mobile amplifiers, run at 14 volts or whatever. It takes that low voltage with large amounts of current and steps it up to a high voltage with low amounts of current, which is your 50 ohm impedance. So the reason that we need capacitors on this transformer is because this does not work the way that you want it to. In an AC transformer, like on your mains power, it works pretty much in a fairly ideal fashion. So you put power in one side, you get power out the other side. There's very little lost in between. There's very little phase difference between the input and output. It works smoothly. But when we're dealing with RF, we have a lot more to contend with. For one, the ferrite is going to be lossy. There's going to be leakage inductance, and there's going to be magnetizing inductance. Now, I know this is kind of a mind bender, and it's some big terms. And like I said, this took me a long time to figure out. So, you know, don't be too. If you're scared, it's scary. You have non-ideal parameters for properties for these transformers. They're not ideal. They don't function perfectly and easily. You can't just plug in a transformer and get, you know. So we have to compensate for that. And each type of transformer, this one versus this one, are going to have different properties. So in an ideal, if they were both perfect devices, we wouldn't have to compensate with capacitors at all. Let's just say, for example, this has a 1 turn of wire going through it. So we have 1 turn on one side and 1 turn on the other. If this was a perfect transformer, we could put 50 ohms into one side and get 50 ohm impedance on the other side. Or we could put 5 ohm impedance on one side, get 5 ohms on the other side. You know, with a 1-to-1 transformer, you should have the same impedance on the on one side that you do on the other. But because of the imperfections, the leakage inductance, the magnetizing inductance, the core loss, the core saturation, all kinds of stuff like that, it's not going to be perfect. So you have to compensate it back to where you want it. And you do that by capacitors. You can do it with inductors as well. You can do it with a handful of different types of components. But capacitors are by far the most common, especially in the HF frequency range. The lower you go in the HF frequency range, actually kind of the less you have to compensate these things. As frequency goes down, things start to work a little more perfectly. Magnetizing inductance, leakage inductance, they don't have such a big effect. But we're right at the top of the HF band, and in the 27 to 30 megahertz range, that's where ferrite transformers start to have issues. Once you get over 30, they really start to become ineffective, and they really start to become lossy. So at 27 megahertz, we're, you know, on the cusp of where these things just don't like to work very well. Obviously they do, and they can, but you're on that borderline there. So each one of these transformers is going to have different properties, and you're going to have to compensate those differently, and that's why there's going to be a different value capacitor. And I've noticed there's a trend in CB amplifiers is that, you know, people always put 1,000 puff capacitor on here, 1,000 puff right here, and then the value on the other side is probably, I don't know what they typically put, but it's pretty much always around the same value. And that's regardless of transformer, and I don't necessarily agree with that. I don't think that you should just slap 1,000 puff on here and call it good. There's ways that you can figure out the ideal value, and I'm going to explain that to you. Let me cut this video and go get a drink of water. I'll be back. It's a long topic. I said I was going for water, but I came back with champagne. It's a Saturday. So before I go any further with this video, I want to make a quick disclaimer here. I am not a professional. I am a hobbyist. Therefore, there is probably going to be some technical incorrectness in this video. There's probably going to be something wrong with it. But with that said, I'm going to try and explain it as best as I can. And I'm going to try and be as accurate as I can. And if I don't know something, I'm going to try and be truthful about that. Most of this knowledge that I've gained came from reading Motorola application notes and data sheets. From what I understand, they kind of pioneered a lot of this stuff. And they have some fantastic application notes and data sheets, and it's mind-numbing at first. But that's where all this information comes from. I think that's where most of the RF amplifier concepts and designs come from, is from Motorola. And a lot of their really old stuff is still perfectly applicable today. But moving on. So I was saying that these are not perfect devices. There's a lot of things that you have to compensate for. I don't have one of these hooked up where I can show you on the Nano VNA, but what I can do is I can go over to the computer and I can show you a simulation of one of these transformers and what actually happens to the impedance when there's imperfections in the transformer. So let's go over to the computer and I'll give you a quick summary of what I'm talking about. Alright, so I've previously tested a bunch of these types of transformers, and this one is a type 61. It's pretty similar to what you might find in a lot of different amplifiers. So I think it's a good candidate to start with. So just for context, we could use this transformer for an input or an output transformer. The fact that it's overkill for input doesn't stop it from working. You could make this transformer work on an input, but in this context, we're going to be thinking about this as an output transformer. So SMA connectors just soldered on there for testing, if you were wondering why that's there. So this is a program called SimSmith. If you're not familiar with the Smith chart, this is going to be confusing. You might want to skip to later on in the video. It might make a little more sense to you then. But in any case, Smith chart is one of those things that you kind of got to understand to really have a good grasp on this concept. So this is a program called SimSmith, and it's a really cool application that you can use to design matching networks and simulate a bunch of different things. And what we're doing is we're simulating our transformer right here. So this plot on the graph, the dark blue is our simulated test result, and the light blue, actually, am I backwards here? Okay, no, I got it. The dark blue line is our simulated transformer, and the light blue line is an actual test that I ran and saved into this program. So as you can see, they're very close to each other. But with that said, this isn't going to give you real world results. You can go in here and simulate things, and it's going to be close to what's real, but it's not going to be perfect. So for the purpose of demonstration, I am going to turn off the actual test results, and we're going to focus on this right here. This is our simulated transformer. So this winding is, this would actually be our output 50 ohm side. So we have to think about this kind of backwards. We've got our generator on the output and our load on the input, but in reality, think about it backwards. So this side would be the antenna, and then this side would be the transistors. So remember that, antenna, transistors. Okay, so this is simulated with 3 turns of wire. So imagine there's 3 turns of wire, which would make this a 9-to-1 transformer. 2 turns is a 4-to-1, 4 turns is a 16-to-1, 1 turn is a 1-to-1. So in a 9-to-1 transformer, in an ideal world, if this was a perfect transformer, we would be transforming from 50 to 5.555 infinity, 50 to 5.5 ohms. So if this was a perfect transformer, that's what we would expect. We would expect to go from 50 to 5.5 ohms across all frequencies for a perfect transformer. But in reality, you can see that this is not a perfect transformer. So we're simulating it with a 5.5 ohm load, and we're looking at the 50 ohm side of the transformer. That's what this Smith chart is it's showing us the 50 ohm side of the transformer. So if this were a perfect transformer, we would have our indicator would be right here in the smack dab in the center of the Smith chart. But this is a simulation of an imperfect transformer, and as you can see, we're nowhere close to where we should be in a perfect world. And that's the purpose of these capacitors. The purpose of the capacitors is to bring this circle down to here, more or less. Let's put some fake imaginary computer capacitors in there and see what happens to our Smith chart when we change the values on the capacitors. So let's take a capacitor here, let's put one on that side, and then let's put one on that side. So this is pretty much what you will see in all 11 meter amplifiers. You'll see one across the one from the wire going through the transformer. You'll see a capacitor from that wire to ground, and you'll see a capacitor across the transistors, across the transformer. And that's what we have here. So as you can see, that made a big difference on the Smith chart. It took our impedance point from all the way over here and brought it down to here. Well, let's just focus on one single frequency. Okay, so in this graph, we're sweeping from, what is it, like 1 megahertz up to like 200 megahertz. So that's what we're looking at on this graph. Let's go to our path. So each one of these lines, it corresponds to one of these capacitors, and also actually one of the capacitors is this little line right here. The other capacitor's there, and the pink one is the transformer. So it's transforming from 5.5 ohms up to here through the transformer, and then down to here with the capacitor. So this green line is the change of the green capacitor here, and this blue capacitor is represented by that little tiny blue line right there. So let's see what happens. What kind of capacitance values do we need to get smack dab on the 50 ohm point? Well, I'm just changing the value of the capacitor here, and now that we're in line with the 50 ohm point, I can change the value of this capacitor, and bam. So basically what we did is we put a 55 puff on the winding going through the transformer, and we put 540 puff across the transformer. And this is the result it had. It took us from way out here in no man's land and brought us back down to this point. So I know this is going to be confusing, but when you're actually testing an output transformer on an amplifier board, you're not going to be measuring from the 50 ohm side. You're going to be measuring from the transistor side. Now, theoretically, you can do it either way. You can measure from the 50 ohm side or the transistor side of the transformer. In this case, this would be the transistor side, and this would be the antenna side. In an amplifier, you can measure either way, but I prefer to measure from the transistor side. And the reason I like to do that is because I don't have to simulate the transistors with a resistor. So when I measure from this point. So I pull the transistors out of the amplifier, and I measure through the transformer and over into a perfect 50 ohm dummy load. And then I use the measurements on this side to get my impedance close to where my transistor needs to be. And once I've got it close to where the transistor needs to be, I'll put some trimmer capacitors across the transformer here, and then I'll also put one from the winding over to ground. And by tuning those capacitors and watching the way that the amp responds to different power input levels, you can get it pretty stinking well tuned just by tweaking those two capacitors. Most impedance values you can obtain, you can get a really wide range of impedance values with just two capacitors, and 90% of the time the value that you need is going to be in that range of those two capacitors. But anyway, that's a quick and dirty simulation of what we're doing here. We're using these capacitors to bring our Smith chart, our impedance, down to where we want it to be. So now that we know how to move it, now we need to know where to move it. And that's another complex topic, but I'm going to attempt to give you my best at it. And please keep in mind that there are many ways to skin a cat. I'm just showing you the way that I've learned and that I've used, and this is something, the methodology of measuring from where the transistors are, that methodology is something that you'll find in the Motorola application notes. So I'm pretty confident that it's a good way to go about things. But let's go back over to my workbench and talk a little bit more about how to figure out what impedances we need to see when we're actually measuring and adjusting our capacitors. All right, so for most of you, this is going to be the meat and potatoes of this video. This is the actual test method that you can use to calculate or approximate your capacitor values. But before we get to the capacitors, I want to show you what kind of impedances we get with no capacitors, what the transformer looks like without any capacitors at all. So let me push this button here. Should have done that a minute ago and prepared better for starting the video. But anyhow, okay. We're right in the middle of our favorite band, 27.2 megahertz. So right now we're measuring the characteristics of this system at the frequency that I think most of you are probably going to be using. Of course, if you wanted to build a 20 meter amplifier or a 20 meter monoband amplifier, you'd be at a different frequency, you'd be using totally different capacitor values, you'd probably be using different types of ferrites, so on and so forth. But what we're looking at right now is the impedance that our transistors are going to see when the circuit is tuned as it is. So on the output side of the transformer, we've got a 50 ohm dummy load. That's what this little adapter is here. It's just a 50 ohm resistor inside of there. I could have soldered one from here to here, just a 50 ohm resistor, would have been pretty much the same result. So right now we're looking at if we were to plug a transistor in here, or a pair of transistors rather, since this is a push-pull amplifier, if we were to plug this in here and turn it on, this impedance on this marker right here is what our transistor would be experiencing. That's the impedance that our transistor would see. Just as a general rule, most transistors are going to want to be straight along this line here. So this line is non-reactive. So if you have a point anywhere along this line, there's not going to be any inductance, there's not going to be any capacitance. It's going to be a non-reactive, resistive impedance. And most transistors are going to fall in that range. A lot of them fall slightly inductive. Occasionally you can get some weird results by going slightly capacitive. But in my experience, most of them fall on this line or slightly above this line. So in this case, what the impedance that we're seeing right now is 5.7 ohms, 5.8 with positive J component, positive reactance. So right now we're seeing basically 5 ohms with a whole bunch of inductance. That's what this point is. So just from my personal experience, that's actually not too far off for that LDMOS chip right there. That impedance is actually really pretty close to what this sucker likes. But for, say, a Toshiba, this impedance is pretty far off. So general rule of thumb, the lower impedance, the more current your device is going to draw and the more power output you're going to get from your device. The higher impedance, the less current draw you're going to get on your device, and the lower the power output is going to be. Obviously, if you want more power, you're probably thinking, well, I should just go lower, 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 lower. Yeah, well, there's a point where your device just blows up. So you always want to start on the safe side of things and then slowly move your impedance down and, check your amplifier, see how it's working. Take a look at it on the oscilloscope, the spectrum analyzer, the power meter, the average power meter, the peak power meter. You have to take all these parameters into consideration. If you really want to make a good amplifier, that is. Anyway, after all that rambling, my whole point is that most impedances are going to be somewhere along this line, somewhere between 50 and 0 ohms. Most bipolar transistors, Toshiba's 2879s, those are going to be down in the 1 to 3 ohm range. So 1 to 3 ohms with a positive, a little bit of inductance to it. Don't quote me on that. If you try those numbers and you blow up your amp, it's not my fault. Different transistors like different impedances. There's always an exception to the rule. I'm just stating some of my limited experience on that matter is 1 to 3 ohms for a Toshiba or whatever. So you're going to want to start probably on the higher end of that. Don't be afraid to start up at 5 ohms and then work your way down. That's generally a pretty safe technique, is to start high and work your way down until you get into a reasonable power output range with reasonable harmonics and all that kind of stuff. But anywho, this is what the transformer looks like when we don't have any capacitors on it, when we don't have any compensating capacitors. And like I said, that's actually really close to what you might want for this LDMOS chip, but if this was for Toshiba's or something like that, we're going to have to compensate this to a lower value and also much less inductance. So let me put some trimmer capacitors on there, and we can take a look at what effect that has on the Smith chart. Hold on, I will be back in a blink. The capacitors have been installed. Oh boy, the further I get into this video, the more I realize that this is a super deep rabbit hole, and I'm not going to be able to cover everything you need to know to do this. But hopefully you can think of this as an introduction to this topic, because there's a lot of things I haven't gone over that can screw you. One of them is taking this measurement without everything hooked up over here. So right now this is just a transformer on a board. As soon as you start hooking up other things, like your choke, You know, if you hook this choke up, your impedance is going to change. You put a capacitor on the other end of the choke, your impedance is going to change a little bit. You connect a piece of wire to this and feed it into a relay, your impedance is going to change a little bit. So if you actually are going to do this measurement, make sure everything on that side of the transformer is 100% installed, including your tuning capacitors. You know, you can save the tuning capacitors to install last, but if you're going to run that into a relay, if you're going to run it into a combiner, actually, you know what, combiners and relays, that's a whole nother topic, man. Like I said, this is a deep rabbit hole, dude. There's a lot of ground to cover. But I'm doing my best here. I can only jam pack so much into a video. You know, actually, I really wanted to make this a part of another video that explained more of the operation of a push-pull amplifier. But I get this question a lot, so hopefully this will answer it. And hopefully, I'm sure you guys have probably learned something by this point. But also bear in mind that there are more ways to skin a cat, and yada yada yada. Moving on, we've got our capacitors installed. And now we can move our impedance all over the Smith chart. We can move it to quite a few different places. These capacitors allow us, like I said, to compensate for the imperfections, the non-perfect action of this transformer. And I've already kind of tuned them to do just that. So if we look at our impedance, I removed all the other markers because all we need is the Smith chart right now. So if you remember when I was showing you on the computer, this is 3 turns on this particular transformer, so it's a 9-to-1. In a perfect world, it would transform 50 ohms on this side to 5.55 ohms on this side with no inductance and no capacitance. And we're pretty close to that. I've been able to tune the capacitors to get us in that range. The thing is most transistors probably aren't going to operate there. Like I said, LDMOS, this LDMOS chip here, it's pretty close to this impedance range. It's in that general vicinity. But your push-pull Toshiba transistors, they're going to be a little bit lower. They're going to be down in the 1 to 3 ohm range in my experience. But you know, don't quote me. Like I said, don't quote me. But let's take a look at what happens when we start adjusting these capacitors. So this one is already pretty tightened down, which means it's a pretty high value capacitor. So I'm going to lower the value of that capacitor. I'm going to do it slowly. And we can see what happens. So our inductance is increasing, and our resistive component seems to be increasing a little bit as well. What happens if I tighten that sucker all the way down? So now I'm going higher value on that capacitor, increasing the value of that capacitor. Our resistance is decreasing, and we were moving more into the capacitive range. So if we, this capacitor, I don't remember what it maxes out at, but we could go higher on the capacitance and probably move that even further down into a lower value, and it would probably kind of go in a circle. Things don't move. Like tightening this doesn't move your marker in a straight line. It kind of moves it in any way it wants. It's a little weird how it works. But before you even plug transistors in, I recommend connecting capacitors in both of these locations. So this one is across the primary of this transformer, and this one is from the secondary output to ground. So a shunt capacitor here, shunt capacitor here. I recommend sweeping through the values, you know, turning these things up, turning them down, and seeing what values you can obtain on the Smith chart before you ever plug transistors in. Of course, if you're repairing an amplifier that's already kind of dialed in, you might want to start with a capacitor that's in the ballpark of what was originally installed there. And same here, see what you get. Let's sweep through this capacitor and see what we get. So this one's wide open, so it's the lowest value it can go. Let's increase the value. All right, so now we're moving kind of back into the inductive range. Let's now that this one's about as tight as it'll get, let's loosen this one and see what we get. Okay, so we've got a pretty low value here, pretty low resistance, but our inductance is still a little bit high. In my experience, Toshiba transistors, they're a little bit lower on inductance, and they're also quite a bit lower. Pardon me, It's the wine coming back up. The resistive value is going to be lower as well. So, the general idea here is to figure out what the ballpark impedance that your transistor is going to need, tune your capacitors, pre-tune your system for approximately that impedance value, or go a little bit higher, because higher is going to be lower power output, less strain on the transistors, all that good stuff. I definitely recommend starting with your marker along the purely resistive line. You want to start with your marker kind of dead smack along this line somewhere, preferably on the higher impedance side of things. And once you're pre-tuned for that, oops, losing connections. Who cares? I'm done with that part. Once you pre-tuned your impedance, then you can install your transistors, fire up your amplifier, and put just a little bit of power in and see what happens. So if you were starting from scratch with a transistor that you've never used before, you're building an amplifier, you have no idea what impedance data is, you know, there's lots of tips and tricks to get you in the right place, in the right ballpark, if you don't even have a data sheet. Like if you know what voltage your transistor operates at and what the maximum current is and what the approximate power output is, you don't need to have a data sheet that shows you impedance numbers. There's tips and tricks to get to that, but I'm not going to cover them in this video. Just know that they exist, and you'll probably find them in the Motorola data sheets. I think that's where I learned pretty much all of these tricks. So if you were tuning an amplifier for the first time, you'd want to, pre-tune it to an approximate value, plug in your transistors, fire it up, and slowly start to increase the power, and see what your harmonics look like, see what your power gain looks like, your input power versus your output power, and then you might want to tune these capacitors on the output transformer to get the maximum forward power, the maximum gain. Something I haven't mentioned up until this point, but this whole process works exactly the same for the input transformer. You're just doing it backwards. So the input transformer might have this capacitor across the transistors, and it might have one from, the wire winding to ground. It probably will. That's how most amplifiers are going to be. And this process works exactly the same going the other direction. So, here. Look at that big old input transformer. So we plug our radio in here, it goes into the transistors, and then we have another transformer on the output. It's basically the same thing. Now there is a difference in your testing method. So when you're just getting your impedance in the ballpark of where you want it to be, the method is exactly the same. You connect your VNA to where the transistors would be connected, and then you run that into a dummy load. So that works both ways for the input and the output. For testing, when you're tuning the input transformer, you want to pay attention to your reflected power and tune your capacitors to have the minimum reflected power. So that shows you that you have a good match. That's a real easy way to tell whether your input match is good or not. Pay attention, put a reflect meter in line, a real sensitive one, like a 5-watt slug or something. Pay attention to your reflected power, and then while your amplifier is operating at a lower power level, go ahead and tune these capacitors. Turn it a little bit, see what gets you the lowest, go over to this one, see what gets you the lowest value, and eventually you'll get it to where it's nearly perfect. If you run out of adjustment range, then you probably need a bigger or smaller capacitor. On 2879s, you should be able to get almost no reflect, but that depends on a few factors that are deeper down the rabbit hole. When you're tuning the output transformer, you can't pay attention to reflected power. Reflected power means pretty much nothing. Deeper down the rabbit hole, why that is. So when you're tuning the output transformer, generally you pay attention to power gain. That's one good way to start. If you're putting 1 watt in, and you've already got your input transformer reasonably well tuned, you put 1 watt in, and you tune these capacitors to get the maximum power output with 1 watt in. And then you go up to, say, 5 watts in, and then you check your tune again. You'll notice it's different. So your maximum power gain at 1 watt is going to be a different value for these capacitors than it's going to be at 5 watts of input. So if this was, let's just say an HG 2879C, you might want to crank your power all the way up to, 20 or 30 watts of input before you tune these. and that would give you the most power gain at higher power levels. So much to cover, man. I'm trying to jam this all into a reasonable amount of time, and I just keep coming up with stuff I want to explain. But I can't. I can't do it. It's too much. I could write a novel, but I don't need to write a novel because, Motorola already did it. It's just not in plain English terms. So anyway, I hope that you learned something from this video, because this topic was so hard for me to understand, and it took months and months of learning. And even with this primer, you're not going to understand everything. And be prepared to experiment. Be prepared to read some data sheets, some application notes, maybe a couple of books. There's a lot of books on the internet that are specifically about RF power amplifiers, and if you Google them, you get them for free. I've got at least a dozen books in my library, full thick-size books on PDF that I found on Google for free. So this is just the tip of the iceberg, but hopefully this answers a hard question, because this is a hard question. How do you choose these capacitor values? It's a tough question, man, and like I said, there's no possible way I could answer it 100% in this video. But I hope you learned something. I hope you got something out of this video, and I'm Sharky. I'll be back with another video. Thank you for watching.